Step into the Coliseum. For Cambridge physics students, the exam room is your arena, and quite frankly, only the fully prepared survive. Welcome to this explainer. Today, we're mapping out the precise mathematical language of motion to guarantee you top marks. Whether you're taking the 0625, 0651, 0652, 5054, or tackling the advanced 9702 syllabus, this strategy session is your ultimate weapon. If you've ever looked at a soaring golf ball, a speeding car, or even an astronaut dropping a hammer on the moon and wondered how to perfectly predict where they're going to end up, you are exactly in the right place. Today, we are completely mastering kinematics, moving from basic speed all the way up to complex two-dimensional projectiles. Let's get right into the arena. Physics is highly cumulative, so we're going to build your understanding step by step today. Here is our plan of attack. First, the language of motion. Second, graphing the journey. Third, the equations of motion. Fourth, gravity and freefall. And finally, motion in two dimensions. Let's kick things off with Section 1. The language of motion, scalars versus vectors. Okay, getting this very first step wrong is honestly the #1 reason students' calculations absolutely fall apart later on in the paper. We see it all the time. A student, let's call him Alex, overloads his answers with raw physics fact, but has absolutely no analytical strategy. He misses this core distinction. We absolutely must separate the quantities that only care about magnitude from those that demand a specific direction. On the left side here, we have scalar quantities, like distance and speed. They just have a size or magnitude. But the fundamental hurdle in kinematics is recognizing that displacement, velocity, and acceleration are vectors. That means they have both a magnitude and a strict, unyielding direction. Let me give you a classic example from our source material. Imagine a toy train traveling exactly one full circuit around a 2.4-meter circular track. Its total distance traveled, 2.4 meters. Easy. But because it finishes exactly where it started, its displacement, meaning its actual change in position from the starting reference point, is literally 0. And if displacement is 0, that means its average velocity for the entire trip is 0 too. You see, vectors only care about the journey's endpoints, not just the mileage in between. Before we continue and look at how this impacts your actual exam score, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. And that toy train perfectly illustrates our next major strategy point. When you are dealing with vectors in these exams, positive and negative signs are not just abstract math. They are literal physical directions in space. An absolute expert study tip to lock into your brain is that a negative sign represents a specific orientation. For instance, if a car is traveling forward at a velocity of 35 meters per second and then slams on the brakes, we say it has an acceleration of negative 5.0 meters per second squared. That minus sign doesn't mean less than nothing. It specifically means the acceleration is pulling in the direct opposite direction of the car's forward travel. It's actively fighting the velocity, actively decreasing it. Don't just write a minus sign because your calculator told you to. Understand what it's doing physically in the real world. Moving right along to Section 2, graphing the journey, visualizing velocity and acceleration. Now that we have our core terms totally locked down, let's translate them into visual data to see exactly what happens to an object over a period of time. Examiners love testing this. Take a look at these two types of graphs side by side. On the left, we're looking at displacement time graphs. If the line is perfectly straight and diagonal, the velocity is constant. If it curves upwards, getting steeper, that means the velocity is actively increasing. Now, the absolutely crucial takeaway here is that the gradient, the steepness of the line, on a displacement time graph gives us the exact velocity. It's literally the rate of change of displacement. Conversely, looking over at the velocity time graphs on the right, the gradient of that line reveals the acceleration. A flat horizontal line, that means constant velocity, which translates to 0 acceleration. But a straight upward sloping line, that is constant acceleration. The velocity is steadily climbing. Since gradients are so critical to pulling the right data from these charts, here is a highly practical mark-saving tip straight from the source notes. If you want to reduce percentage errors in your exam calculations, and trust me, examiners look for this, always use as much of the straight line as possible when measuring that gradient. Don't just pick two tiny points that are right next to each other on the paper. A tiny triangle magnifies the slight error of your pencil point. Stretch your measurement triangle all the way across the graph to ensure maximum accuracy. This is how top students squeeze every single mark out of a graphing question. And here is a brilliantly simple trick for those velocity time graphs that will save you massive amounts of time on the clock. To find the total distance an object traveled, you don't even need to touch a complex physics formula. Just calculate the physical, shaded area directly underneath the line. Let's say you have a 650-meter journey of a cyclist, like the one we're tracking here. By simply breaking the space under that line into basic geometric shapes, calculating the area of the rectangles for constant velocity and the triangles for the acceleration phases, you can easily tally up the total displacement. It's an incredibly elegant strategy that bypasses the heavy algebra completely. Section 3. The equations of motion. Calculating the unknown. Having visualized the motion, we now enter the absolute heart of kinematics. This is where we solve for exactly what we don't know using the famous 4 equations of uniformly accelerated motion. Consider this table your ultimate exam cheat sheet. Notice how there are 5 total variables across these equations. S for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time. But here is the massive secret to never getting stuck on a problem again. Every single equation in this table is missing exactly one variable. That's by design. Your job is simply to look at your exam prompt, identify which variable you don't have and don't care about, and pick the matching formula. For instance, if the question doesn't ask for displacement and doesn't give you displacement, just use the top equation. If you don't have time, jump straight to the bottom one. It's a perfect system. But you need to take very careful note of this vital constraint. You can only deploy these specific equations if the acceleration or deceleration remains absolutely constant for that specific part of the journey. If the acceleration is changing, like a car braking harder and harder as it approaches a stoplight, or air resistance increasing as an object speeds up, you cannot use these equations for the whole trip. In those cases, you'd have to break the journey up into smaller segments where acceleration is constant, or use completely different methods. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back to the strategy. We frequently see students, let's call one Sam, who constantly rush their exams. Sam spots a kinematics question, skips reading the command words, and just starts blindly throwing numbers at a calculator. Don't be Sam. To completely avoid those careless errors and guarantee your marks, always follow these 4 procedural steps. First, write down everything you know in the margins. Second, clearly identify the missing variable. Third, select your targeted equation from the cheat sheet. And fourth, substitute and solve. But pause right there. Before you substitute, check your units. A devastatingly common mistake is forgetting to convert units like kilometers into meters or minutes into seconds before doing the actual math. Always sync up your standard units first. Section 4. Gravity and free fall, vertical motion. So let's take everything we've just learned and apply it to a real-world environment. Whether it's a tiny feather or a massive anvil, if we completely ignore air resistance for a moment, gravity pulls absolutely everything down toward the Earth at a perfectly constant acceleration. And that magic rate? It's 9.81 meters per second squared. Because it is a constant acceleration, it beautifully unlocks all 4 of those equations of motion we just talked about. You can use them to perfectly predict vertical drops. Now, what's really fascinating, and what the examiners love to test you on, is how you handle a complex situation, like the stone being thrown upwards off a cliff into the sea far below. This is where vectors demand your absolute respect. You must strictly define one direction as your positive baseline. Let's say we define upwards as positive. That means the stone's initial upward velocity of 6.0 meters per second is a positive number. But gravity is pulling down, meaning your acceleration instantly becomes negative 9.81. And here's the kicker. Since the sea is 12 meters below our starting point, the final displacement is a negative 12 meters. If you don't logically lock down those positive and negative signs before you start plugging numbers into your equation, your final answer is going to be completely reversed. You'll lose the marks. And just to prove that this kinematics framework isn't just an earthbound rule, let's look at this brilliant conceptual question. Objects on other planets or moons also fall with equal accelerations to each other, but they don't fall at Earth's 9.81 rate. The moon has way less mass, so its gravitational pull is much weaker. This is exactly why an astronaut dropping a hammer on the moon from a height of 1.2 meters watches it fall in seemingly slow motion compared to Earth. The amazing thing is, those 4 equations of motion still work perfectly on the moon. You just swap out the 9.81 for the moon's specific freefall acceleration value, and the math solves itself. Section 5. Motion in 2 dimensions, the parabola. We have finally graduated to the very top of our kinematics tower, two-dimensional motion. This is where objects are moving horizontally and vertically at the exact same time. Assuming negligible air resistance, any object thrown or launched at an angle is going to follow a beautiful, symmetrical path called a parabola. And the absolute master secret to solving these high-mark exam questions is splitting the initial velocity into two completely independent components using basic trigonometry. You isolate the vertical physics and you isolate the horizontal physics. The absolute most crucial point to grasp here is that we treat these two erections as two totally separate math problems that just happen to share the exact same clock. Let's take a golf ball hit at 45 meters per second at an angle. Step 1. Resolve that speed into its upward and forward components using sine and cosine. Step 2. Use only the vertical component to figure out how long the ball is in the air. Remember, gravity is pulling it down, so it's going to decelerate, stop momentarily at its absolute peak, and then fall back down. Step 3, while all that vertical drama is happening, the horizontal component is just cruising forward at a constant speed because there is no gravity pulling it sideways. Let's see exactly how that plays out in an exam scenario. Because the horizontal velocity remains completely constant and the flight path over level ground is perfectly symmetrical, the math becomes incredibly elegant. If your calculations show that a golf ball travels exactly 100 meters horizontally just to reach its maximum peak height, you know instantly, without doing any extra math, that it will travel a total horizontal distance of 200 meters before it finally hits the ground. The upward journey and the downward journey take the exact same amount of time. Symmetry is your best friend here. Now, because these 2D problems require multiple sequential steps, like finding the vertical time and then plugging that time into the horizontal equation, you run a massive risk of rounding errors compounding. To keep your final answer perfectly accurate and secure the full marks, remember this pro tip directly from our source notes. Always keep an extra significant figure for your interim values while you're calculating. Do not round off early. Only round down to the final required significant figures at the very, very end of your problem. Look at the immense ground we've covered today. We have successfully built our kinematics tower from the ground up, starting from the basic definitions that distinguish scalar and vector quantities. We visualized those concepts on dynamic graphs, learned to systematically navigate the uniform acceleration equations, applied them to the relentless 9.81 meters per second squared of Earth's gravity, and finally, we resolved complex two-dimensional parabolic flights. You now possess the strategic, mathematical language to describe almost any moving object the examiners can throw at you. I want to leave you with this final, critical thought before you head into the arena. Considering that a single missed negative sign can mean the difference between calculating a stone flying high up into the air or sinking straight down into the sea, how are you going to adjust your personal exam strategy to respect the absolute power of vectors? Kinematics is a beautiful, precise puzzle, but it demands your full, unwavering attention to direction. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams, your Cambridge success starts here.